All right, hi everyone. This is our last video in the particle in the box. We were talking about the 2D particle in the box. In the previous one, we wrote the Schrodinger equation. We solved it. We got these wave functions and energies. And in this video, I want to talk about how we interpret these results. The first thing I would point out to you is that this is a different system. It's a 2D problem. Particle can move in X and Y. And when we solve the solution, right, we get two quantum numbers, nx and ny. Right? Two dimensions, two quantum numbers. And those two quantum numbers arise from the boundary condition in the X and L dimension. Right? That goes to 0 at the edges of the box. The way we typically write this would be something like this, psi sub 1, 1. If you see that kind of notation, that means nx equals 1 and y equals 1. And once you denote that or you catch that notation, then we're going to do the things that we normally do, which are to sketch the wave function. I'm actually not going to do that because I can simply show you some computer generated files here. But let me point out something to you. So along one coordinate, these wave functions look like particle in a box wave functions. Right? It's a separable system. So if I called this X and I called this axis Y, and I'm going to work in two different colors to try and make this as clear as possible. If I looked along any dimension here, along the Y axis, it would look like the psi 1 one-dimensional particle in a box wave function. Right? If I looked at any dimension along the x-axis, right, it would look like a 1D particle in a box wave function. And when you start to put this all together, right, you get this type of representation, right? So this is psi 1, 1, the lowest energy wave function for a particle in a box. Now there are other wave functions, psi 2, 1, right? Look at this one. Here's my x-axis. If I were to look along here, right, I should put this in here, nx equals 2. The wave function you can imagine would look like this. Whereas along the y-axis, this would look just like the lowest energy, n equals 1 particle in a box wave function. So you can start to get this imagery. The other thing you can start to see is that there is a psi 2, 1. There is also a psi 1, 2. Right? And this one is exactly the opposite. Along this dimension, x, it'll look like the 1D particle in a box wave function. And along y, it would be the opposite. Okay, so along any one coordinate, it looks like the particle in a box wave function. Now, this starts to bring up some other issues that you might pick up on. These are topographical images of these wave functions. It's the same idea. What you'll notice is that there's an inherent symmetry between the 2, 1 and the 1, 2. They're sort of turned 90 degrees from one another. And given that that's true, right, that their wavelengths are in some sense the same, it suggests that their energies are the same. And we'll see shortly that that's also true. The other thing I would point out to you is that rather than nodal positions, when we have two-dimensional problems, we now have nodal axes, right? These are entire lines in which the wave function is 0. So those are the wave functions. The other thing to think about is the energies. And here is our energy equation. I suggested last time that when you derive these energy equations, what you should do is draw an energy level diagram. And so we're going to do that again. For simplicity, I'm going to measure my energy in h squared over 8 ml squared units. There's 0. Right? And what we're going to start looking at are different nx, ny combinations which produce energy levels. Right? The lowest energy level would be 1, 1. Right? And that would give me 2 of those energy units. The next energy level would be 2, 1. It's 5. And you'll note that this is also, I get 5 energy units with 1, 2. Right? And this has a specific name, which I hope you've heard before, which are called degeneracies. Okay? So these are degenerate energy states. And one thing you should know is that when you see degenerate energy states, it suggests that the wave functions have a high degree of symmetry, right? Like psi 1, 2 and psi 2, 1. These keep going. So let's see, this was 2, 1. I guess the next one would be 2, 2. That would be 8 energy units. The next one would be 3, 2 or 2, 3. Actually, it would be 3, 1 and 1, 3. It would be 10 energy units. So on, and so on. And at this point, I want to pause and point out one last thing, which is that these energy levels are sort of fundamentally different than the 1D system. In the 1D system, the energy levels got further and further apart. There's only one combination, so those energy levels scaled as n squared, and they got further and further apart. The formal language for that is to say that the state density decreased. State density is the number of states per unit energy. But in 2D systems, there are competing effects. One is the n squared. So again, this is pushing the states further and further apart. But the other is that there's now multiple combinations of numbers which produce the same result. Right? So these degeneracies are pushing the numbers closer and closer and closer together. And these are competing effects. And we're not going to talk at all about it here, although maybe we'll a bit later in the course or perhaps in some of the applications. But this has really interesting implications for quantum confined systems. If I could make a two-dimensionally confined system, you get some really interesting results with regards to their solid state physics behaviors. Okay, I think that's all I wanted to say. Yeah. And so I'm going to stop here. That will be the end of our particle in a box discussion. and I will conclude Unit 1. See ya.